Well, hello everyone, and welcome back to our fifth session. Can't believe that our year has gone by so quickly already. This is the final installment of the unpacking of the grade 6 curriculum, the new one, and want you to give you some things to think about for what your needs might be moving forward, that you've gone through the curriculum once. What do you see now as your next steps? What do you see as being sort of the important pieces that you want to unpack in year two? So keep that in mind when you get your survey question. It gives you an opportunity to give some feedback, and it helps the consortia to know what we can do to plan to support you. So to that end, we are on session 5 for Math 6. And we're going to be unpacking some of the things that we said we would be leaving to the last session, specifically algebra. The last part of algebra was the big one. And then we left patterns because we needed to finish the algebra so that patterns made more sense to the students. So it was kind of a sequential order anyway that we needed to follow. And we're also going to touch a little bit on the last one, which we left completely for now, which was statistics. So let's begin with our land acknowledgement. In the spirit of reconciliation, we want to acknowledge that this gathering is taking place on traditional lands across the province of Alberta, home to many diverse First Nations, Métis, and Inuit peoples. We acknowledge that this land is a traditional meeting ground, giving voice to its original peoples and the story of creation of this country in a way that history may have forgotten. And the image that you're seeing there comes from an art image, and it's actually based on an expression that can generate some of the patterns that are within that. So the link that I have for you at the bottom is called Indigenous Art, but it takes you to, for most of you, going to be a familiar site, and that would be to Stanford Education, the U Cubed site. And this is an excerpt from a visit that Joe Bowler had with 3 Indigenous teachers that came from Alberta, and they're still obviously teaching in Alberta. And in this document here, we won't go through it all because in the interest of time, I'm going to leave this to you, but the hyperlinks in the blue here, they've provided you with a lesson plan, and just to give you an idea of how they incorporated the art into the expressions and patterning that was going on in the classroom. It's an interesting read and really interesting to hear what these ladies from Alberta have been doing. So I hope that that's something that you find interesting and helpful for you down the road. Okay, so I don't have a problem with spacing, but I really wanted to highlight the fact that we left that last part of algebra, the solving of equations, for a couple of reasons. One is that people weren't ready, they said, to go into the last one, which was using sort of algebra tiles. And so we'll do that today as best we can virtually. This is always definitely better to do in person. And then how we start using our knowledge of expressions and equations to solve the world of patterning. And in particular, we're looking at setting up tables of values and using the expressions that we come up with to fill in those tables of values, and can we graph those points, and etc. And then also looking at statistics. What is it that we're supposed to be doing in grade 6? And not that it's necessarily all new, but the language is definitely going to be new. So something for us to get used to using, and sort of getting things going on the right foot. We can see that grade 7 probably will have that same new language once the new curriculum comes in. So now's a good time to start getting used to using those terminologies. Okay, so let's have a look at algebra. Now, we had a bit of a snag here earlier today with whatever is happening, but for some reason the machines were shutting off and shutting on. So hopefully we're going to be scot-free this time around. But if so, if it happens to power out, we'll just come back on the same Zoom link, just giving you the same insights, and we'll pick it up from wherever we left off. So for algebra, because we left the third component of that, the solving of equations, not that it's really components, but we left that part to the now. I just want to quickly touch on where were we at as far as covering the grade 6 so far. So in grade 5, remember that in algebra, it starts in grade 3, grade 4, they talk about order of operations, and they talk about those 4 operations of multiplying, adding, subtracting, dividing. But we don't talk about variables. They have open boxes, they have symbols, emblems that they use to replace what we would call a variable. In grade 5 is where the language of the algebra came into play. So the constant term, the variable, gets defined. We talk about coefficients. So we talk about all of those components. So now we're using expressions that have variables in them, and we're going to be using equations that have variables in them. And so that would be grade 5. But grade 5 was limited to what they could do for the solution to equations, because a grade 5 student does not know integers. So I could give them a question such as a 1 or 2 step question that might be something like x plus 4 equals 6. Because if I'm going to use manipulatives, I could take the 4 units and remove them. And if I'm using the preservation of equality or a balance scale idea, what I remove from the left side to keep it balanced, I'm going to remove the same 4 on the right-hand side. I can do that with that type of a question, but I wouldn't be able to give them that in grade 5 if it said x minus 4 is equal to 6, because I have no way of interpreting for them what that subtract 4 would be. They don't know what a 0 pair is. We're going to work on that again today. So in grade 5, we said you have to be somewhat cautious that when you're setting up your equations, that you are setting up equations that require only have addition in them and multiplication, so that the student is doing subtraction and division, and neither one of those should end up being a negative value in any way, shape, or form, or a decimal fractional value. So for the variables, so we want to just be cautious of that. But by the time we get to grade 6, because before I'm going to do anything with equations, I will have already done the work on integers, and I would have done work on fractions. So all of that's already living in the background. Students know how to add and subtract positive and negative numbers. So I don't have any restriction in that regard. However, we're not going to have negative variables. So from there, it's a matter of expanding what their knowledge already was from grade 5, the foundational pieces, and moving it forward to incorporate all fully the integers. So we're including things like adding like terms together. So same variables, I can add the coefficients because I already know what a coefficient is. I already know that I can write not x plus x, but I can write it more efficiently as 2x. I don't go 2 times x anymore, 2x. So in grade 5, they've learned that that multiplication can be written in a shorter way. So we're starting to get much more refined in what our algebraic equations and expressions can look like. So in grade 6, when we started off with the order of operations, we had 4 operations in grade 4. In grade 5, we just kept those same 4 operations, but we introduced parentheses. And in grade 6, we just bumped it up one more level, and we introduced exponents. So they've really just progressed all the way through till they got to grade 6 with exponents. We're suggesting, again, that when we teach order of operations, to keep in mind that it isn't about giving me a mnemonic or an acronym for how I'm going to do this, and that's the lesson of order of operations. It's understanding the concepts of why we do it the way we do. Can we model a picture to show them why it is that this is how I have to get the answer for the multiplication before I can get the answer for the addition? So that's an important piece. And that's what this slide is just reminding us of, is to ensure that we just remember that it's not about the acronym, it's about the concept. And so we really, really want to make sure that we are seeing that piece happening and it's going from there. Some common misconceptions that the research is showing us right now is that some of our students, they definitely benefit from having a mnemonic or an acronym, but that memory aid that they're getting sometimes just gets memorized in that order. So if M came before D in the short mnemonic that you gave me, that's what I believe it to be. It has to be multiplication before division. They're forgetting that it's multiplication or division, whichever comes first from left to right, and then the same thing for addition and subtraction. So that's what the caution is. So the common misconception sometimes comes in when you're using that is that the students just believe that that is the order. There's no flexibility there. So when I look at how might I model this, if we go back to what we did in grade 5, we wanted to show them what it would look like if I was going to introduce parentheses, how might that be modeled for a student? And we're not going to model every order of operation question, but it's important that they see it. Like, what does it mean to say what is in the bracket needs to be done first or in the parentheses? So here I have a green bar and a red bar, and whether I know the values of those or I've never even worked with a Cuisenaire rod before, it doesn't really matter. I can put a grid on the background. I can see what the value of the green is. It's 6 units long. So I have a 6 add a 2, and I have 6 plus 2 3 times over. So this is a repetitive quantity. So rather than writing 6 plus 2, add 6 plus 2, add 6 plus 2, which you could do for sure, but it just becomes more tedious, more cumbersome, and chances of me losing a number or forgetting to add something along the way always exists. So when I have a repetitive quantity, I can take that quantity and count how many times it shows up and use my brackets instead, or use my parentheses. So I have 3 groups of 6 plus 2. So 6 plus 2 sits in here, and there were 3 groups of those. I have this one lone value of 5 that's sitting out at the end. And that's being added to all of this, not to each one. There's just one of them. So that means I need to kind of figure out how many of these do I have all together, and then I can add that lone one at the end. It would be wrong for me to say I'm going to add this one to this, and to this, and to this, because there aren't that many of them there. Could I have done this differently? Could I have said I have 3 groups of green, 3 6s, and I'm going to add 3 groups of 2s or reds, and then I'm going to add the yellow? And the answer is of course. So I could have written it this way, but I could also have written it this way. This simply tells us what this would look like if it was expanded. So that makes it just that much more valuable for me to also show them what the properties were that we were talking about before. So this gives us a way to model, and this is what we did with the grade 5 groups. So I can expand on that kind of thinking now when I start adding some of the things in that we had from before. So just if this is new to you, just to give you a bit of a pause here for a second, if we look again at how we wrote the repeated values, we used our parentheses or we used multiplication, then what does that look like on the next screen when we go through and we ask, okay, how would you write this one? I've got these 2 light greens, I've got these 3 pinks, and I've got this 1 brown at the end. So just give you a second to look at it. You can just jot down what it would be. You don't have to put it in any chat block or anything. Just what would you write down as your expression that would model the top one? And then if you've got just a second, go ahead and do the bottom one as well. And there's definitely more than one answer. So below that, you can see what possibilities, and again, one's not more right than the other, but if we're trying to be efficient, we really would like to use the brackets where we can. So 2 times 3, that'd be 2 of the groups of greens. Each of those greens was worth 3. So I've got 2 sets of those. And I've got 2 sets, sorry, of the, oh, I think I'm missing something in there. I am. I've got 3 times 4, and there should be a 2 in front of that. My apologies. I should have had a value in there. I'll have to fix that before I put that into your folders. So when I go through and put these in, I'm going to make sure that I'm going to model these together, and I'm going to get the value for these. So it's going to be 2 groups of 2 times 3, and I've got 2 groups of 3 times 4. Or in some cases, people have added these together and they've made them into one. Whatever, there isn't necessarily one only answer here. And often we'll give students questions like, here's a string of numbers. there's an equals at the end, where would you have positioned the brackets? Or would you have rearranged the numbers in such a way that the answer would come up to be what it was? So again, well, that's the kind of thing that we want them to look at. Look at the bottom one. I have a 10. I have 2 groups of 5. And if you're not familiar, again, this represents a subtraction. I have the length of a bar, and I'm taking away this amount of that distance. So if this represents 6 and this represents 2, then I need to make sure that I do this subtraction, 6 minus 2, before I add that value into my expression that's over here. So I have 10 add 2 groups of 5, and I'm going to subtract the 10 or 6 minus 2. Could I have put this in brackets? Yes, you could have, absolutely. But does it have to be? No, because if I know my order of operations, I know that I'm going to have to do that first. So it's important, I think, that students understand and see what those might look like. These are typical examples. We're not saying these are the end-all be-all. These are just examples. They come from the CPAR document, so there'll be lots more in there for you. But these are examples of what I would use in grade 5, where I'm using the 4 operations inclusive of the brackets or the parentheses. So what do I have to make sure a student knows? I can't jump into algebra if I haven't done integers. I also can't do algebra if I haven't done fractions, because fractions can be part of our order of operations. And so it's really important, and same thing with the decimals. All of those pieces need to be done before I jump into these. Could I do them sections at a time? And so as I introduce fractions, now I bring back another order of operations questions and expand on them? Of course. Integrating them back and forth and repetitively bringing them back over and over as we learn things is a great way for them to maintain the thinking that we have. So as I move into grade 6, there's a couple of things that we're considering that we wanted to put forward. And I say we because I'm talking in terms too of globally from the CPAR documents. When we look at when we analyze what is that curriculum statement asking us, there's some implications. One of them was what we just talked about. You know, what do I have to make sure they know before I can actually craft one of these expressions for them to do? So you can't ask me to do F, for example, if I've never done adding and subtracting of unlike denominators. That's not going to work, obviously. But equally as well, remember that when we introduce exponents, those numbers can get very big very quickly. So we are suggesting, because they do questions like area and volume, those are questions that they're already using squares and cubes. So a suggestion is that we use a maximum of the power of 3 or a cube. So we're going to focus on keeping sort of all the organizing ideas that use that strategy or that concept of multiplication for area or multiplication for volume. We're going to keep that sort of intact as we work through the order of operations as well here. So using squares and cubes is great. Could I give them a question like, what is 2 plus 2 plus 2 plus 2 5 times, and ask them to write it as an exponential form of 2 to the 5th power of 5? The answer is of course. But just keeping in mind that with exponents, numbers can get big very quickly. And as I start multiplying, we don't want this to become just a routine bit of multiplication just because they can. We want it to have value of what it is we're trying to give them as far as the concept of an exponent. So these are some suggestions that we're putting forward, and we're just saying that a reminder, this isn't just a complete download from grade 7. We aren't using any negative bases in these questions. All of them will be positive natural numbers. There'll be no fractional bases, so I'm not going 1/2 to the power of 3 or cubed. So we're going to limit those numbers, and the bases are restricted to being natural numbers. Decimal addition and subtraction is limited to thousands. We don't want to get larger than that. We do thousands in grade 5, hundreds in grade 4, so that would be reasonable. Addition and subtraction of fractional numbers definitely can go in there, but there's no multiplication or division of the fractions. Like you're not doing 1/2 times 1/4. You are doing 2 times 3/5 or 11/9, that you can do because you're doing that in grade 6, where they're taking a natural number and multiplying by a fraction. So this is where the curriculum really does have some sort of set things that we need to be aware of. It doesn't mean I have to do things just in a certain order, but definitely if we're not going to be cognizant that there are some pieces in number, there's pieces that I need to have completed before the students get here, there's going to be some struggles along the way. And we're going to have students saying, I don't know how to do this. And it's only because they haven't gotten there yet. The order of operations was started in grade 4, parentheses in grade 5, and you do exponents in grade 6. So currently in grade 7, we also still have some negative, like we'll have bracketed -2 squared. So we would have students explain to us, how is -2 in parentheses squared different than -2 not in parentheses squared? That still maintains to be a grade 7 question and does not come into grade 6. I hope that kind of clarifies a little bit of the questions that we've been getting about, like, how far do I go? The other piece is that in grade 6, we are looking at simplifying. So the word simplification, simplest form, simplifying an expression comes into play. And that means that I could be adding like terms. So whether it's like terms with variables, or the fact that I've got numerous constant terms in there that I need to add, I will simplify it down so that I get it in as lowest a form as I can before I do something with it, whether I'm evaluating, substituting a value into evaluated, or whether I'm going to solve an equation, whatever that might be. So again, you have these opportunities here that we would look at, and some examples. Any one of these, and it doesn't necessarily always have to be X's. For those of you who've been doing the math for a while, we know that we tend to go to an X, but that doesn't mean it always has to be an X. It could be M's and T's and S's and whatever else you want it to be. Just a note, when you're typing out and doing things with variables with students, that variables tend to be in italicized form and always in lowercase, so that they learn to very quickly notice that they do look a little different, and therefore there is no confusion between a multiplication sign at any time. So lowercase and italicized is the sort of the standard way that they're presented and put forward. So let's look at the part that we haven't done yet in grade 6 algebra. And that is, it says all simplified forms of an equation have the same solution. So whether I have 2x plus 3x plus 4 equals something, or I write it as 5x plus 4 equals the same number, those two are simplified, but they're both going to have the same answer. When I evaluate them, I will get the same answer on both sides as well. So we're looking to simplify wherever we can, and where we can add like terms together, we will, before we move forward to go through the process of solving. So algebraic expressions on each side of an equation can be simplified into equivalent expressions to facilitate solving, making it as simple and easy as we can. So in this case, when I look at this picture here, I have 3 cups. I could use C for cup. And instead of writing it as C plus C plus C, I could say I have 3C subtract 4 is equal to 8. So that would be the simplified form of that particular illustration that we're seeing here. So there's many ways that we can solve equations. There isn't just one manipulative that works. There's lots of them. You can use this idea. You can use the balance scale approach. You could use algebra tiles. Lots of people use the balance scale approach with an algebra tile so that students are moving them from side to side, or removing them from side to side and keeping it even. It's one thing for us to say, do to one side what you would do to the other, or make sure that both are balanced by what you do to one, you do to the other. All those little sayings and nuances are absolutely true and absolutely correct. But if I'm not a mathy person and I don't get math and struggle with it, those are just words. So the more you can show me and let me actually physically do it to really solidify that, the better off I'm going to be. So we're going to look at some examples. We are going to go into a deck where you can start to work with the algebra tiles. And when we do anything that has to do with integers, signed variables, we always have to have a legend, and that's important for students to get used to seeing. So if I look over here, for example, I see that I have a legend at the bottom, that the reds right now are negative values, and the yellow and the green are positive. And we'll unpack what those are if you're not familiar with them. But really, what we're trying to do is make sure that we use all the work that we did with integers. And I'm assuming that everyone has done that, but I'm going to touch on that a little bit just to make sure that if you haven't done that kind of work with the manipulatives to show students how to add or subtract the negative numbers or positive and negative numbers or integers, I'm going to show you a couple of examples of that, just so that it's really clear about how does that link into solving equations. So if I use this balanced approach, here's a good simple equation, and it would be a great one to bring the money out right off the bat, right? If I can have them show me $18.50, and I could use a pattern block, pick a hexagon, that could be your manipulative for your variable, is equal to $22.25. And I want to know how much did I have to add to the $18.50. So if we say that really to solve the problem, how can I figure out how much money that hexagon was worth? Well, there's two ways I could do it. I could say that I'm going to go 22.25 subtract $18.50, and whatever that difference is, that would make up this number here. Some students, especially with numbers, but for some students, they hate subtracting. And so for them, counting up is better. So for those of you who've been around where cash registers used to be there and you didn't have something telling you how much change you were going to get, you would count up. So I'm trying to count up to 22.25. So in this case, I'm going to go 18.50, another 50 cents takes me to 19. I count up to 20, another 2 cents or $2 gives me 22, and then 25. And then whatever I've counted up, that's the change the person was getting. So that was the way we went from doing the subtraction, literally, to simply giving them the same difference that they would have normally had. That's one way. It's not the only way of doing it. But that's a premise that some students prefer, and there's nothing wrong with that. But in the end, what we're trying to do is we're saying, here I have this question, and I want to be able to solve for whatever that unknown is. So just without getting into decimals onto the balance scale, it's a very simple equation. I have x plus 4 is equal to 7. My legend says that x is this value right here, and it's positive. I don't see any negative scales here. I see that this is a positive 1. So to represent the left-hand side, I'm going to put a variable. It's right there. I'm going to put 4 individual units, and they're stacked. They could be stacking cubes. And on this side, there were 7 of them. There's no variable. There's just the 7 units or cubes. So something in hiding in this side of this variable would be the same, that would give me the same values on both sides. And yes, the students at grade 6 will look at this and say, well, it's 3. Yeah, but can you prove to me that it's 3? Can you show me how you could get 3 without just pulling it off the top of your head? So if I remove 4 of these cubes from here, that means this will be heavy and it's just going to drop down. This is going to go up. We've changed the weight. So to get it back balanced again, I need to take 4 of them off of here as well. So that would leave me with just the variable and the value that's over here. This is what we call preservation of equality. I want them to stay equal on both sides. So every time I make a move, I preserve equality. I did not change this balance. It's not tipping in one direction or the other. So in this case, I have the variable x, and that's what I want to know. How much is x equal? X is equal to 3. 1x equals 3 of these cubes. Now I can go back and I can verify. Verify means to take the answer you think is correct, put it back into your equation, and to do that, we suggest showing students to put the number into a parentheses or a bracket, because as somebody looking in who didn't watch what you were doing, this kind of signifies for them that you are verifying by substituting. There was a variable sitting here, and the bracket is telling me that I am substituting a number in for that variable, and now I'm going to add the two together, and I show that both sides are equal. So it's just a sort of a way of indicating that I've solved. I'm taking an answer and putting it into what used to be a letter sitting there. I hope that makes sense to everybody. So in the world of algebra tiles, and you may have these in the school but not have used them before, they come in all different colors now. They used to have kind of a standard color of green uh, on one side and white on the other, and the little ones were red and white on and combinations. But anything that was white was negative, and anything that was dark was positive. But I could have flipped those around on any given day and said, today white is going to be positive and dark is going to be negative. So that's why we say the legend is really important. People need to know, what am I working with? What's the positive value? What's the negative value? And that's important because we end up creating what we call zero pairs. So just to very quickly go through to make sure that everybody's on the same page of what that comes from or where did that come from. I just want to go back and do that because if we haven't, then we can't go through the algebra piece very quickly. So I'm just going to bring this one up as well. And you have access to this slide deck. It'll be inside your slide deck. And I'm not going to go through all of the front matter. It introduces integers to students. Basically, an integer can be created by setting up almost like a tug of war. And that's kind of the way I present it to students when I'm teaching in junior high at the moment. I'll say, you know, blue team, yellow team, whatever team you're blue, you're yellow. And if everything's equal and managed and nobody's pulling with any extra force, if I put a ribbon right here, they're pulling that way and these guys are pulling that way, this ribbon isn't going anywhere. And that's the most perfect true tug of war that you can have. If we kind of equate that to integers, it helps students to understand where does that go and what does that mean as far as number lines or numbers themselves. So if the blue team's pulling this way and everybody's pulling with the same force and the yellow team's pulling this way, then every person on this side is the same distance away on this side. He's pulling with the same force. He's pulling with the same force. Ribbon's not moving. We kind of cancel each other out in our pull and nothing is happening. The ribbon stays put. That ribbon is like our zero in the middle. It's like saying this is the starting point to going to the blue team or going to the yellow team. But clearly, as I say to students, you can't have a blue team and a yellow team because somewhere on the other side of the world, they have no idea what blue team and yellow team means. So to have a conventional understanding, anything to the right of zero is what we call the positive numbers. So the blue team was the positive numbers. And the yellow team, just so that I can tell them apart from the blue team, were called the negative numbers, not to make them negative in any way. And so I see that I'm having a distance from 0 to 1 here. That's my first person. I have my distance to the person on this side. So these are people pulling in that direction. These are people pulling in that direction. And they're all pulling with the same distance, same force. In grade 6, when you do integers, you talk about magnitude. And magnitude is the distance from 0 to a location that you're given, whether it's 0 to 2 or 0 to -2. Doesn't matter. But magnitude is a distance. So if someone says, what is the magnitude of -5? We don't say, oh, because I went over here, it's -5. The distance is 5. I went 5 units and I happened to go 5 to the left. So magnitude is not negative in that regard. So that's how we introduce this. And the next couple of slides just go through applications of positive and negative numbers, some examples. I want to get to this part here. These are the traditional algebra tiles, the way they used to be colored. You can still get them. They're not gone. But now they also have blacks and reds and blues and whatever. So it's a matter of you identifying what it's going to be. So in this case, everything that's dark is positive, could be a place to start. If I flipped every one of these over, they'd be white on the other side. So it gives me a consistent white would be negative. But when I start with variables with students, I could start with just grabbing a handful of pattern blocks and just having them on the desk and saying, you know, if you were going to clean these up a little bit and put them into some kind of organization, what would you do? Well, chances are that you would probably put what's the same color and shape together. And that's the equivalent of having like terms. That's really what you're doing, is you're saying what looks the same size, same color, same shape, goes together. So I can add hexagons with hexagons, trapezoids with trapezoids, rhombus with rhombus. But I can't take a rhombus and a hexagon and add them together and smush them into a new shape. That doesn't work that way. We can't add X's and Y's and get an XY. That's a new letter combination we've never had before. There's no shape to go with that. So that's a common mistake. And if we can start with this kind of an idea, then we maybe sidetrack the students who tend to make that mistake of, oh, I can add this to a trapezoid and that would give me these 4 plus 1 is 5. 5 what? 5 yellows, 5 reds, 5. It doesn't work. They're not the same. So that's the whole idea behind getting into like terms, getting into variables. So I'm going to skip through this. You're welcome to go through it and have a look at it. But what we want to do is get into some of the important facts about those tiles that we're going to work with. So for us today, I'm going to say anything that's a dark color. And when we do the other ones, I've got them labeled already. So on this sort of trial run that we're going to do, anything that's a dark color is going to be a positive. Anything that's a white color is going to be a negative. And when we look at these big squares right here, these don't come into play in grade 6 because they are values of variables squared. This is an x squared, and we're not doing that in grade 6. So we park those big ones for now. We're really only concerned with the long rectangles and the small squares. So the long rectangles represent a variable. In most cases, we call it an x. It doesn't have to be an x, but generally that's what you're going to find is the long rectangle is called an x. The lighter side to it is the negative x, the flip of it. The small square that's a dark color is a positive one. The flip side of it would be a negative one. So for every, just think of that number line. For everything I have that's positive, I have an equal part that was negative. This allows me to use variables. This allows me to get constant numbers or constant terms in my expressions or equations. So I have the operations that I can do to solve equations available to me because of the signs that are on there. So for us today, colored is positive, white is negative. So the magnitude question, if I put a red square that just fits between 0 and 1 here, and I pair it with the flip of it, turn it over with a white square, I really haven't done anything because that's what's covered here has been kind of just covered in the opposite direction there. And that's an important piece. When you think of the tug of war, and that's usually what kids think of as the tug of war. When I pair a unit that's negative with a unit that's positive, same size, opposite color, I get what's called a zero pair. They canceled each other out. -1 and +1 together didn't do anything to the ribbon. It stayed at 0. If I took +2 and -2, I'm still not going anywhere because they canceled each other out. There's still 2 people they pulled that way, 2 people pulled this way. Ribbon stayed put. 0's not moving. And that's one of the reasons that we say 0 is not part of the positive side and it's not part of the negative side. It separates the 2 sides, but it's not positive or negative. It's neutral. It's the ribbon. It didn't belong to either one of the 2 teams. So in this case, we could ask which one of these would give us a 0. Would these 2 give us a 0? They're same size, opposite color? Yes. These ones? Yes. These ones? Yes. These ones? No. These are 2 white ones. These are 2 people pulling in one direction. There's nobody opposite them. So no, this is not going to stay balanced. So those are important for students just to get ideas like that. And they catch on very quickly when you have the manipulatives in front of them. Which one of these would give me a 0? This one would, because I have a positive and a -1 together. They're going to give me 0. This looks like it's a negative. This is a positive, but they're definitely not the same size. So this isn't going to give me an answer of 0. That's a definite no. If I were to put these 2 together, that would be a yes. So you're getting the idea that same size, opposite color would give me a negative. For every positive, negative that I have, I get 0. In this example, I don't have another negative to cancel out that positive. So these guys are 0, but this guy's still there. So it's positive. So this will not give me 0 as well. All right, so let's move on. Just to make sure that if we understand all of that premise, your algebra tiles could then be used for students to model for you. And you just call them out really quickly. Show me +2. So they're going to show you 2 red ones. Show me a +3 and so on. So we're calling out these numbers and the students are quickly demonstrating, just laying it on their desk and you can go through them fairly quickly. When they're all positive, easy. right? That's what you hear the kids say, oh, this is so easy. Okay, then we go to -3. So show me -4, -5, whatever. They're all white. So again, once they understand that a negative is represented by a white, and these are units, so I'm not using the rectangles, I just have to count out how many you call out. So all positives, easy. All negatives, also easy. So what happens now if I wanted to get into something like adding those signed colored numbers? Well, this is a grade kindergarten question now. What is +2? And we don't always write a positive when they're positive numbers, but for our purposes today, we will. What is a +2? In other words, 2 reds, add 3 reds. So if I'm using my tiles, I can count them. It's going to be 5. And we've always known 2 + 3 is equal to 5. Now I can verify it and show it to somebody. Okay, what about if they were 2 white ones? -2, add a -1. So 2 white ones, add a white and below that, and I'm going to end up with a -3. I'm missing a number there for some reason, not coming up. There it is. So white plus white still give me white. Okay. So we ask students to give us, do they see anything? As they're doing these, and you could be calling a whole bunch of these out. Just as soon as they do one, everybody's got it, thumbs up, let's move them back, let's call out a new one, they do a new one. Eventually what you'd like to do is be able to ask, are we seeing a pattern? And that pattern meaning when I had red plus red, I got red. In other words, positive plus positive gave me positive. When they were all white, I only got whites. There's nothing else I could have put down there. So white plus white is white. So negative plus negative is just going to give me more negatives. And always put it in context. I borrowed $3. I now borrowed another $2. So I now owe $5 so that they understand this context isn't just about white squares. Give me an example every time you give me a question. But what about when we mix them? So when I have a -3 and I'm going to add a +2, I already know from my tug of war that for every white that was pulling opposite a red, nothing happened. They equaled each other, and that gave me 0. So if I were to line up those that I know are 0 pairs, well, 0 added to anything doesn't change its value. So for all practical purposes, once I find a 0 pair, I can get rid of that 0 pair. I can just pull it right off of my desk or off of my page, put it aside. What I'm left over with is a -1. So think about it. I borrowed $3. I paid you back 2. I still owe $1. And that's what this is showing. So again, giving me a context about how that works. So now I'll try it again. So we say, I'd like you to show me -6. And below that, I'd like you to show me +4. So they're going to show us 6 whites. They're going to show us 4 reds. And whenever I can find a 0 pair, without being told, from here on in, you're always going to get rid of 0 pairs. You're looking for things that I can partner up. Well, I've got a whole bunch of them here that I can get rid of. For every 0 pair, I can remove it because adding 0 isn't changing anything. And I end up with -2. I borrowed $6, paid you back 4, still owe you 2. All right, so that's an important component of what we do when we are working with equations as well. That's not going to be any different. We need to make sure that they understand how to get a 0 pair, because that helps to preserve that preservation of equality when we're trying to keep left side and right side balanced. So in this question, I have -2. I want to add +4. So I have way more reds. Here's my 0 pairs. And I end up with getting rid of my 0 pairs, and I end up with an answer of 2. What you will hear students say already at this point is when they see the question, they'll say it's going to be red. You'll hear them say that it's red, or it's going to be white. And so when I hear that, I say, how do you know that? How do you know that it's going to be that color? Well, because you got way more reds than you do whites. It'll be red. They don't always have an answer of how many reds yet, but they know what it's going to be. So they're already starting to process that the larger the sign is going to be the sign of the answer as well. And that's good thinking. That's where we want them to be. So in this one, they would say it's going to be a red answer. And some of them already are picturing this without actually laying it out. And that's where we want to go. But we don't want to rush this. This isn't a one-day thing with algebra tiles. You don't just get rid of them after we've done it for a little while and just say we're done. They should just be out there. Kids use them as much or as little as they need after they've shown you proficiency. Once you feel comfortable that they know they can answer all these questions, then we're good to go. Okay, so that's an important piece. We'll do one more question or one more section in here that would be important for us to know, especially when we're doing questions for solving equations. So let's build combinations of +3. +3, I could put 3 red ones out. That would be not a problem. So here's my 3 red ones. But it's still +3 if I add a 0 pair, because that's 0. 0 to anything is still that number. So I could put another 0 pair in there if I wanted to. I could put another 0 pair if I wanted to. I could put a whole bunch of 0 pairs. I could put as many as I could possibly fit on my table. And I still haven't changed the value of 3. And that's important for us to know when we do subtraction. When you are doing integer subtraction, students need to know this notion exists. This approach of finding values of a number without changing it because it's a 0 pair can be leveraged when I'm trying to do a subtraction and I can't take a number away that something I don't have. So for example, here's some numbers. We could say, give us some other ways that you could write this. They could show a negative white, or a white one, sorry, and then a 0 pair, or they can show white one and 2 0 pairs or whatever. So all the different combinations, lots of them. There's endless. There isn't just one that they can come up with. But where does this play a role? It plays a role, as I said, in subtraction. So let's have a look at, can you take away +2 from this amount? Oops, sorry, where's my amount here? Okay, there we go. For some reason, I've got these timed backwards. So let's just go through the question first. It says -3, so I've got 3 whites, and I'd like to take away a +2. I'd like to take away 2 reds from 3 whites. Well, that's not going to be happening right away because I don't have any reds that I can take away. So if I keep in mind that I can add 0 pairs to anything without changing its value, then if I added 0 pairs, that's the missing parts there. Here's my -3. I wanted to take away 2 reds, don't have them. But if I build in my 0 pairs, now I have 2 reds that I could slide off my desk and put away. So if I took these off now, that would leave these 2 still sitting there, which means that my answer will be 5 whites. So think about that for a second. You had $3 that I owed somebody, and now I'm actually going and borrowing 2 more is really what I'm doing. So I end up owing you $5. So this idea of building a 0 pair sometimes helps me to get the color or the value that I need to take away that isn't already there. Let's try another one. So I have -2, and I want to take away a +1. I don't have a red one, so I'm going to build a 0 pair. And I apologize, I'm not sure why this timing is off here because that wasn't the case before. If I take that away, I take my red one away, that will leave me with the 2 original whites, the white one that came from the 0 pair, which leaves me an answer of -3. Okay, we're really having a problem here. So the difference is -3. Let's try another one. If I have 2 whites and I want to take away 4 whites. I had 2 whites. I want to take away 4 whites. So I didn't have 4 whites to start with. But if I build 0 pairs, I can take away those 4 whites, take them off my table, and I'm left with 2 reds. So if I owed you $2 and you interpret this way, I take away a debt of $4. In other words, I overpaid you. You're to the good $2. That's really what this is saying. You also have an outcome in grade 6 that says subtracting is the same as adding the opposite. So if you think about that for a second, that is saying if you had -2 subtract -4, it would be equivalent to saying -2 add the opposite of whatever comes behind it. This is negative, will now become positive. Would a negative 2 and a positive 4 give me 2 reds? And the answer is yes. We know students like to add more than they like to subtract. So given that's true, you can show that to students. So for those who struggle with subtraction, they can change their subtractions to addition of the opposite. And for most of them, that just kind of it makes it clear sailing for them. Okay, so let's go back to our slide deck. And we have these tiles that we're working with now. Remember, we're not going to use the big ones. The X is still green. The negative of that, so you can see it with a white background, is going to be this reddish or this orange one. There's my positive and there's my negative. So I'm going to put this in the chat box so that you can join along, save it to your computer. And this is almost like a balance scale for us. We'll just do a couple of quick questions on it. We're not going to do a ton. So let me throw that in the chat box for you to grab. And you'll have access to it when you get the slide deck as well. So as I'm building this, we always say once you've built the equation starts in balanced forms. In other words, whatever I put here and here to start with starts balanced. And then it's up to me to do the solutions to the things that I need. So let's say, for example, my question was, let's just start small and we won't get too big with the numbers either, so we don't have to drag too many things over. So I'm going to say, let's show x plus 2. So here's my x. Positive 2 is the yellows. So there's my x plus 2. Let's go equals 4, just to make it a quick one. Okay. And so I'd like to know, what is the value of x? What's a single x equal? And on right now, I don't have a single x by itself. I don't have it isolated. I don't have x and then the number. I have x added to something right now. So in order for me to remove these positive 2's, we just did a whole bunch of work of how do I make them 0? Well, I can make them 0 by partnering them up and turn them into 0 pairs. And if they're going to be a 0 pair, I just changed the balance. I tipped it down to this side because I put something here that this side didn't get. So to keep it balanced, preservation of equality, I'm going to move 2 of them into here. Now I haven't added anything different on either side. I'm still balanced. These are all 0 pairs. These are 0 pairs. So that means that x will be equal to 2. So just to, this might be a little bit more tedious than we want it to be. Doing it hands-on will be much faster. I may just drag them off in the next one. Come on, there you go. There are other formats that we can use this for, but as I said, having them directly in front would be the way to go. So the value of x is equal to 2. So does 2 plus 4 equal 6? The answer is yes. Does 2 plus 2 equal 4? The answer is yes. And that's what we started with. X plus 2 is equal to 4. X equals 2. 2 plus 2 is 4. All right, so let's change this one up. So I'm going to, let's try another one. Let's do 2x. Let's do one that's a little bit longer this time. 2x. And we'll go minus 1 is equal to, I don't know, whatever, 3. Let's do that. So 2x minus 1 is equal to 3. So this is a negative 1. I don't want 2 x's. I just like to know what 1 x is, but we are doing the order of operations in reverse because remember, adding and subtracting comes at the end. But in order for me to solve, I'm actually going to do that first. I'm going to move those first and then come back to the variables. So this is a negative 1, and in order to move the negative 1 to a 0, I need to partner it with a positive, make it a 0 pair. But now I've added something to this side. I again changed the weighting. It's going to make it imbalanced. I better bring the same amount over on this side. So these 2 are gone. I'm just going to drop them down here just to make it faster. So now I have 2 x's is equal to 4. So I can either divide both sides, 2x divided by 2. 2 divided by 2 is 1, so that's 1x. But if I divided the left side by 2, I would have to take the 4 that I have here and divide by 2. If I want to show it visually just to start with, what I want is an equal share, and we talked about that in fractions. What is an equal sharing? Well, here we go. Each one of the x's got 1, still some left over, so this one gets 1, this one gets 1. So 1x is equal to 2. So the algebra tiles have lots to offer, and students do really well. Those, especially those who struggle with the notion of, I don't understand what subtracting a negative is, or I don't have to add a pot, like they don't get that part. This takes care of that for them, because all they really need to focus on is building a 0 pair, and they're still maintaining that preservation of equality on both sides. So I'd encourage you to find where those tiles are in your school and see where they are. You've got them here that you can access them free as well if you need to go online. But they can't be any better than what you see really in front of you when they can move them and slide them on their desk. So this is just another example of what I would show. X plus 6 equals 15. We're using inverse operations as stated in your curriculum document. The inverse operation of adding a 6 is a negative 6. And what do? I pair them up to make 0 pairs. Once I have the 0 pairs, I can get rid of them. And then I end up finding my value. In this case, the value is equal to 9. So I hope that makes sense, but don't hesitate to reach out if you need some clarification on any of those. Okay, so let's look at patterns. And a lot of people, when we first started the 4, 5, 6, they said, patterns, why is it at the end? Like, we should do it at the beginning. We always do patterns at the beginning. And we could normally have done a lot of that there, but you now see what kinds of things they have to know. Well, patterns even more so. They're going to be doing expressions. They're going to be doing positive and negative numbers. They're going to be dealing with fractions. All of that has to be covered first. And I really have to understand how to solve an equation or to evaluate an equation. That all has to come from algebra. So the pattern better sits right now towards sort of the end after I've done all those, or if I'm going to do all that stuff up front, then it kind of falls in line with it. So in grade 4, they talk about sequences of numbers. They talk about triangular sequences, square number sequences, and we unpack all of those. We talk about the difference between an arithmetic, so adding to get from one term to the next, versus a geometric, so multiplying to get from one term to the next. And we talk about how there's a specific one called the Fibonacci series sequence, which is an example of a pattern of sequence of numbers, but they have a very special relationship with what we have in the world today. They call it the golden rectangle. It's a proportion that comes out of that sequence of numbers. We get a proportion of a ratio of about 1.6. And that 1.6 is an aesthetically pleasing proportion. And so we're not going to go into that right now. You could watch this, but this outlines for you, just first of all, if you've never heard of that term before, what is that sequence? So what does it mean? They'll outline this a bit more. The one below has better examples, but there's no talking in the one below. So I need to understand it first to make sense of what the pictures are showing me. So they kind of go hand in hand, and they're really well done. But again, just having a look at those might be helpful. So examples of square number patterns, we talk about arithmetic or geometric. We look at sequences of numbers, and what we're seeing is, how did I get from the first number to the second number to the third number, and so on. And sometimes that first number, second number, third number are given the term of the sequence. This is the first term, it was 0. The second term, second position, is 2. The third position was 4. The fourth position or fourth term was 6, so on. So we'll use those in grade 6, that terminology in grade 6. But right now for grade 4, they're just deciding as whether I'm adding or whether I'm multiplying to get from one term to the next. So that's what they unpacked in grade 4 without going through all of the detail that was there. We look at in grade 5, more specifically, looking again at arithmetic sequences and then looking at what is their term. So this is where that comes in. And you'll see that we use the letter T for term. Again, could it be something different? Sure. But you know, T, term, they fit, so it's easy to remember. And we use a subscript to represent that this is the first term, this is the second term, the third term. These aren't powers, they're just subscripts to identify position. And so are those required for grade 5? No, but in the language that we sometimes use with the students, it makes sense to show it to them. They don't have to learn how to write it. You're not assessing them on it on any way, shape, or form, but just so that they understand it. And so what we ask them to do is figure out, if I know the first 5 terms, can you tell me what term 8 would be? In other words, can you tell me what the 8th number in the sequence would be? So that's what they are unpacking as they go through in grade 5. We ask them, can they figure out what the rule is? What is the rule that you're using? Well, I'm adding 2 each time, and this one I'm adding 5 each time. So they have to express what the rule might be. And that gets used in grade 6 when we start figuring out, when we figure out tables of values, and we try to figure out the rule that's going to be used to fill in that table of values.
You want a baked potato?
So here is the example of where I have a figure, and the figure allows me to say, in figure 1, how many dots do I use? I had 2 dots. In figure 2, I have 3 dots. In figure 3, I have 4 dots, and so on. This table of values helps me to organize information that might be presented in a graph. So I have a column called figure number, could be term number, depends on what the question is. And in this case, we were asking them to reflect on the number of dots that they see. So I see a pattern that starts to grow. I could ask them, what do you think the next figure will have? What would figure 5 or 6 have? Figure 6, because we already have 5. What would they have for the number of dots? And so on. As we fill in our tables of values, we can also take these tables of values and start to plot them on a graph. So again, before I can do patterns, I have to have done coordinate geometry. The students need to understand grid ordered pairs. They need to understand how to label that. They need to understand that horizontal moves go before vertical moves, and so on. So again, it's that important connection of, what do I need to know before I get here to make sure that it's kind of a seamless flow to go through. In any case, when I look at a table of values, the very first column represents what we called the X values when we were doing coordinates over here. The second column represents the Y values. So this first column of figure number 1 with 2 dots could be written as 1, 2, or the order pair 1, 2, which would mean that figure number is on the bottom, number of dots on the side, 1, 2 would be right here. This one would become 2, 3, and so on. If these are in fact arithmetic, or if in fact they follow the same pattern consistently, we're not going to join them. But when we put these points on a grid, you will find that the points start to follow a pattern. They're following a straight line. If you have a whole bunch of them that are straight line, and then there's one that's hanging down here for some reason, and then the rest of them keep going, this is not a pattern that is consistent. So to be an arithmetic pattern that consistently adds, or what we call the common difference in this case, or is multiplying to get something, we want that pattern to be consistent. And to do that, I will see that by the points as they are lined up on the graph. So those vertical points. So these are taken also from the CPAR document. So you'll find examples like this in there as well, that you can use with the students, or just for yourself, however you want to use them. Remember, CPARs aren't required, but they're just there for you to get extra resources if you need them. So here's another example. I don't always have to start at 0. I could say, here's the 3rd term, and I got this number. Here's the 4th term, here's the 5th term, here's the 6th term. Can you tell me what the 1st term would be? So can they determine what the number is? Can they figure out what the relationship is between the term and the term number? So if the term number is 3 and the term was 24, the term number was 4, I got term to be 32. The 5th number was 40. The 6th number was 48, and so on. What is the pattern that I'm seeing? Well, I'm seeing that if I multiply the term number by 8, I will get the term. So 8t or 8n or whatever you're going to call your variable is your term number. Then if I multiply it by 8 each time, I get that value. So that's just an example of how we're going to use patterns as we move through. So again, for us in grade 6, we talk about a variable that can be determined as values are changing in quantity. So that's, how do I see the quantities change? What change is occurring? Is it getting bigger? Is it getting smaller? Most of them that we're going to do is they're going to get bigger because those are just a little bit easier for them to do. So in grade 6, we use the term function as well. And that is new. We haven't put that one into the curriculum before. That's usually in the upper grades. But a function is nothing more than using that rule, finding that equation that's a rule, and using that to create what the pattern is going to be. So I put a number in, it got chommed through that rule that we had. Maybe I was adding 5 to whatever I put in, and out pops an answer. So sometimes that's called an input-output machine. You put something in, something happened in the middle, and something came out. Put another number in, something happened in the middle again, same thing, and you put another number out. And that rule of something that's happening in the middle, that's the rule that we want students to be able to figure out. What's the rule that's being used for the number that comes in to the number that comes out? What's that pattern that you're seeing? So it's an extension of what we just did, right? We're asking them to think through how that's going to look. So a table of values will help me do that. Maybe I'm going to make a table of values if I have the rule, or I get the table of values and I'm asked to find the rule. Either way, whichever way it's going to go. The values of the independent variable. So the number that I throw in is independent. The X number that I'm going to drop into the machine is an independent variable. The number that pops out is dependent on whatever I put in, and whatever the rule is inside as it's being added or multiplied inside and pops it out. It depends on whatever I started with. So X will then become the independent side and Y will become the dependent side. And this ties very well into our science conversations that we have as well, right? They have those words of independent and dependent variables as well. Same idea. So I'm doing an experiment. I control this part of it. That's my dependent variable. I put it in, I set it up. But what happens is the independent. It's dependent on whatever I gave it or put in or whatever that case may be. So students need to be able to identify the dependent and independent variables in a given situation. So that's what we're looking for. They need to be able to find the rule. So what's happening inside that machine, or what happened from the X column to get to the Y column? Can they represent those values of independent and dependent as coordinates on a plane? So can they plot them as an ordered pair? So we know that the first column is my X value, the second one is my Y value. Can they write an expression that represents the function? In other words, what is happening is a function. It's a function of time. I put a number in and something happens and I get something out. And then determine a value of the dependent variable of a function given the corresponding value of the independent. So in other words, what if they gave me all the Y's and I had just a couple of X's missing? Do I see a pattern enough that I can figure out what's happening on the dependent side? So filling in missing values in sequences of functions, that's really what they have to be able to do. So can they put it into a table of values? Can they identify the rule? Can they identify missing numbers on either side? In other words, fill in missing numbers on a table of values or in a term of sequence of numbers? And then can they plot them? And it says investigate strategies for determining a value of independent variables of a function given the corresponding. So I'm really looking for patterns, and can they solve some problems that would fit into that? So going along with what I've been saying, this is an example of an input. You want to go and get a juice or a pop out of a machine. You input money, that's a function. Your output is depending on what button you pushed and how much you put in and whatever it was, out comes this pop. So that's the idea. Something goes in, it makes a decision, or there's a rule that's happening, and out comes the product that I'm looking for. So functions are not just in math. This is an example of a function. If you travel a distance over time, I travel to a certain place, and it takes me this amount of time. How much did I travel in each hour that I went? That's a function. That's what we call a function. It's something that's changed over time. And if I know that I can go 110 kilometers in 1 hour, and I'm traveling for 3 hours, how many kilometers will I have gone? Then I can multiply that 110 by 3, and I've gone 330 kilometers in 3 hours. I've used the rule of 110 times hours, tells me how far I've gone. This is what we call a function. So it's not really, some people said, oh, it's a lot scarier sounding than it is when you actually get going on it. And that's true. It really is. So in short, what we're really saying is you have this machine. If you think about it like that, you put something into it, number, something happens, which is the equation, and out pops this output. So I have these input columns, I have these output columns. And what we're really looking for is what's a value, what kind of an expression could I write in here that would help me to get these numbers? So I put a 2 in, I got a 7 out. I dropped a 3 in, I got an 8 out. I dropped a 4 in, I got a 9 out. So what happened in this machine to get these numbers? So it looks as though I'm taking the X, or the input number, and adding 5. And if I check it, that's correct. So I would assume then that when I put 6 here, I'm going to get 11. So I would write in here X, the input number, plus 5, or whatever letter you want. Doesn't matter. It doesn't have to be an X. I just put X up there, so that's why I'm using it. So the expression that I could put in here as my output would be X plus 5. So if you said, well, X is 100, what is the next number? What's the output number going to be? It will be 100 plus 5, or 105. So this is getting to the whole piece of what we just talked about, what a function is. What's the rule? X plus 5. X plus 5 is happening inside the box. So there's an example here of shelves and bookcases. For every bookcase I have 4 shelves. If I have 2 bookcases, I have 8 shelves. So it's like saying for every bookcase times 4, it'll tell me how many shelves I have. So I could use whatever, B if I want for bookcases. So B times 4 is equal to the number of shelves that I have. So if I had 4B here, where this is my B column, 4 times 1 is 4. 4 times 2 is 8. Okay, if I had 5 bookshelves, I'd have 4 times 5, I would have 20. And what some students will do is they see the pattern of adding a number on, they'll verify just by adding it down. And that's fine, there's nothing wrong with it. Again, I could write them as an ordered pair. My bookcases will go down here. So 1, 2, 3, 4, 5 bookcases, and then whatever I need for a scale that's going up the side. So I hope that's starting to make a little bit more sense, so that students can just sort of navigate through this. But if they've done that work already in algebra, this is the natural extension of that. It's just we're not just doing algebra tiles. It's not just X's that we're looking at. Now the variables can suit the context, like B for bookcase, or C for cats that are coming in and you're going to feed them, or whatever the case may be. So we just have these variables that we can use that make a little bit more sense. So without going through all of these, there are some additional examples. So there's some questions that we could ask. Again, I could make a table of values for here. Here's another one where it's asking you to figure out what the rule would be. Here's what it looks like when some of them are graphed. So again, you get a sense of what that might look like when we talk about different functions. Okay, let's finish off the last piece, which is statistics. So in statistics, when we look at grade 5, that's a good place to start. They took the data that they've collected from their question, survey, whatever they've done, and they learned how to do frequency. In other words, they might use tally marks to say, you came through the door, you gave me this answer, I put a mark down, put a mark down, put it in. For every 5, they put the grouping of 5. And so they figured out the frequency, or the count of how many of each data value there was. They used what was called categorized data. So if I had asked the question, what's your favorite fruit? And maybe I'm going to even limit you to, these 5 fruits. Of these 5, or maybe one of them is none of the above, what would you respond? And then I put my tally mark down and I work it out from there. So then we determine the frequency of each category would mean that they would add up how many people said they liked apples, how many said they liked oranges. Was there one that stood out the most? Was there a tie between any of them? Like there was 37 people that liked bananas and 37 people that liked apples. I mean, it's not unlikely that we could get a tie, but it's not likely either. The mode is the number that shows up most often. So in this example that I just gave you, where 2 fruits had exactly the same amount, both of them were at 37. We would say the mode or the number that showed up most often here was 37. So that would be a possibility as well. Okay, what type of fruits, what juices do you have, that type of thing. Language, remember I said at the beginning, there are some language changes. So we have closed list questions and open-ended questions. So closed were questions where I limited what you could respond to. You didn't get to just pick anything. You couldn't say mangoes because it wasn't on the list. So this would be an example of a closed list, whereas this one would be an open one because I'm just saying, what's your favorite fruit juice? You can tell me whatever you want. I have to write it down. If I already have it on the list, I can give you a check mark or a tick mark or whatever. But every time somebody gives me one that isn't already given, I'm going to add it to the list. So that's part of what we unpacked in grade 5. We also looked at the categorized data now has to be represented somehow. So how do I represent that? I could use bar graphs, dot plots, stem and leaf plots. So these stem and leaf plots were new in grade 5, but the bar and dots were not. And so, or sorry, that might have been grade 4. But these graphs have been used already in primary over time as well. So students would be well versed with them. A lot of the questions that they're being asked throughout the grades is to compare the data as it's represented in each of the graphs. Does a graph give you an advantage, one graph give you an advantage over the other by the way the data is presented? Does it tell a bit of a different story? And so again, if you're not familiar with any one of these, or you're never done a dot plot, which is right here, you've got some quick how-tos at the bottom that you can watch, or the students can watch if need be. Sorry. So here's an example of frequency table. So I did my tally marks and they were talking about hours instead of doing every minute to the minute. They grouped the question to be anybody between no homework to half an hour a day when you get home, how many students there were between a half hour and an hour and so on. So here were the numbers that we saw. And the one that showed up most often was that 1 hour to 1.5 hours that had the most responses in it. There are some questions that you can find here. These are hyperlinked for you, so you can go in and get some additional ones. The only thing I would caution you on is and these come from these are grade 7 kinds of questions, so that's where the references are going to come from. But when you go into those grade 7s, they're also going to talk about median and mean, and we're not doing that in this grade yet for the curriculums. So you'll have to just ignore those and just look at the mode questions that you have. So just additional examples that come from there as well that you could possibly use. Are you allergic to any of the following animals? And again, students might say, no, 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 and still be allergic to them, right? So maybe even having an F, which is none of the above, or yes, but none of the above. That might be another way of finding out, oh yeah, there are people who are allergic, but not to any of the ones that we listed. So just having students have discussions about what kinds of questions they're asking and are they really encompassing the people that they're asking the questions of. We move towards, in some cases, the total. So in this case, 22 students were asked how they get woken up or how they wake up in the morning. And this plays more of a role when we get into grade 6, because in there, we're going to talk about taking those frequencies, taking the answers that we got, how many had in each group, and working that out as a percentage or as a decimal of the total. So here's where some new language is going to come in. Relative frequency can be used to compare the same category of data across multiple data sets. So I know this is a little bit faint, but I was looking for an example that gave me sort of the whole thing. I didn't want you to have to hunt around and get different volumes. So we're just going to do one big example to sort of unpack this. So relative frequency can be represented in a number of different ways. And one of them could be a fraction form, one could be a decimal form, one could be a percentage form. Data can be organized into groups or categories. So in this case, let's just look at the question first so we know where we're going. Katie asks 10 of her friends whether they prefer chocolate, vanilla, or strawberry ice cream. And here are the 10 responses. It doesn't matter what order they're in, but each child's name is there and what they prefer to have as an ice cream flavor. Our skill is to interpret the frequency, which one shows up, which one's their favorite, which one do they like the most. of that categorized relative data and express it as a fraction, decimal, or a percent. So let's have a look at what that might look like. Here was the information that I just shared with you. So I can set it up in a table, again, just like we did before. And in this case, I've got my first column are all the different flavors of ice cream. The frequency could be those tick marks, or I just count the number of people that answered by that. So in this case, the frequency of chocolate was 5, of vanilla was 3, and strawberry was 2. The relative frequency would be based on how many people she asked. Well, she asked 10 friends. So 5 out of the 10, or decimal 5, or 50%, whichever way they're going to express it, or you ask them to express it, 50% of the students preferred chocolate. So in our frequency that we've just done, this was by far the most preferred flavor by students. The second most preferred was vanilla, 30%, or decimal 3, or 3/10 if I want to do fractions. And strawberry came up at the end. These should add up to 100% because that's what we are basing it on, is the total number of students who were asked in the question. So relative frequencies, in other words, kind of the experimental approach, is once I did the experiment and got the data, here's the results that I got. Students equally likely outcomes of an experiment have the same chance of occurring. So we want them to explore things that are unbiased. So if I have a normal 6-sided die and I roll that, I have 6 numbers on 6 faces, and the die is completely legal. It's not unbalanced in the way it was made. Any one of those 6 numbers could come up on any roll. It's not that because I rolled a 1 the first time that I won't get a 1 the second time. Every one of them has an equal chance of coming up. So they're exploring this, and they just give some examples: heads or tails on a coin, the roll of a die, the results of spinning a spinner. So if the spinner is equally spaced out, like you see here, or colors, and I spin it, if the spinner is not faulty in any way or weighted incorrectly, any one of those numbers should have the same likelihood of occurring. So that's what your second stats outcome or cusp line is talking about. So identify the possible outcomes of an experiment, like what could happen. That's the expected outcomes would be what we used to call the theoretical. I expect that if I rolled a die 6 times, that I would get the number 1, 2, 3, 4, 5, 6 once each in the perfect world. When I actually do it, though, that may not be the case, right? And we know that. So we can use the predictability of 1/6 to say, if I rolled it 100 times, about 1/6 times 100, so 100 over 6 to the nearest roll, which they can do in grade 6, tells me what I would expect to have happen. Now, we can say that's what we expect. Then we try it. We do 100 rolls of the die. We record all the numbers that come up, and maybe we are close, but maybe they're not. Maybe one number showed up way more often. So that's the difference between our expected and our relative frequency. And using all different kinds. So I did include just an example here that we might want to use that has a bit of a solution so you can see it followed through. But identify the possible outcomes, and then collect the categorized information, predict the likelihood, determine the relative frequency. So in this case, we did a drawing of a card. And what happened was they had 25 out of a possible 30 that turned out to be numbered cards, and only 5 turned out to be face cards. So relative frequency, let's look at what's the relative frequency of the numbered cards. What was the probability given the 30 that we had? 0.83, 0.83, or sorry, 0.83 or 83% came out to be a numbered card. And if you think about it, it should be higher for the numbered cards because there's more of them than there are face cards. That we got 5 out of 30 is considerably less. So 5 out of the 6 possibilities, or sorry, 5 out of the 30 possibilities is what I would get for the relative frequency of a face card. So it just gives us a little bit of a different way of being able to express the results. It's not totally new to the stats that we've been doing in the past. As I said, the language is a little bit different, and that's going to take a little getting used to. And it would be prudent for us to use the new language so that as they move into grade 7, they're using that language. Next year, of course, will be a little bit different because we still have the old curriculum, but that's okay. I've included a few other pieces in here. These are just some links that you'd be able to use for additional resources. Ontario created a spreadsheet of resources for their teachers based on grade and based on strand. So when you go in here for choose statistics from the top, and you'll see all of the grades, but they've given you a descriptor in each box saying, here's what you'll find behind this box. All of these will be about frequency, or all of these are about probability or whatever. So you can choose if there's something you want, then what you'll get is tasks, additional videos that you can use, additional activities that you can do with the students as well. So this is just an extra section of resources for you. And then I've also included a link for just virtual manipulatives. So we've gotten a few emails of people asking for, are there places that we can go to get these? There's lots. And if you just Google what you're looking for, virtual manipulative, and just name it, you'll get them come up. But this is a nice compilation of them, and they've kind of broken them out by grades as well. And this is an activity. It deals specifically with the kinds of things you're doing. So if you're looking sort of like a task approach or a PBL approach, this is an activity that you could maybe include. Just have a look at it and see if that fits into what it is that you're doing. So wrapping up for the year, we have basically 2 months left to go. So you will be getting that emailed survey as always, but it's also a time for you to think about then what are the needs then that you have with the new curriculum now that you've been through it once or will have gone through it once. What are the holes, the gaps, the things that you might still need? Is it resources? Is it assessment? What is it? Or maybe not. The CPAR documents, remember, those are found on the ARPDC website, and there are more of those coming up now for 456, so just keep checking back to see what's been posted, and there'll be a good number of them there. Here are the links for you for New Learn Alberta for the ARPDC site. And if you have not yet downloaded the verbs document, you might want to do that, because remember that we had a team from the ARPDC work on the definitions of the verbs and give exemplars where possible. And it just helps so that we're all sort of talking the same language when we interpret those verbs, that we're not doing something very different than somebody else might be. So it just provides a little bit of continuity there. So thank you very much. Thank you for your time throughout the year, and thank you for all the hard work that you've been doing throughout the year in unpacking the math. And for those of you also unpacking the science, we've appreciated working with you. And I wish you all the best for the remainder of the year and a wonderful summer if I do not see or hear from you before then. Thank you very much, everyone.